Assalamualaikum. Very good morning to all of you. So for today's video, we are going to continue with lecture 16, which will be covering the topics of Ampere Circuital Law. So kindly please have a look at the following excerpt from the course information. This is our planned topics for week 9, in which the following topics will be as shown. We have the first topic of Ampere Circuital Law, in which we're going to learn about the application of Ampere Circuital Law in calculating the magnetic field intensity for the symmetric current distribution. And following this, we're going to have a look at the curl concept, the Stokes theorem, and magnetic flux density. But for lecture 16, our concern will be only on the Ampere Circuital Law. Okay. Right. So for lecture 16, this will be the topics which is on the ACL. So reference for this lecture 16, you can get it from Sadiku, page of 302 to page of 309. So the motivation of this lecture 16 is for the students to understand the concept of Ampere Circuital Law, ACL, and its application in calculating the magnetic field intensity. Right, so this is a comparison with the Gauss Law, which we have learned it in electric field topics before, electrostatic field before. So basically, ECL is analogous to Gauss Law. If you base on the screen, you can see that for the previous electrostatic field study, we learned that the Gauss Law can be applied in calculating the electric field intensity for the case of special charge distribution. Okay, where we have learned that the Gauss Law can be applied if your charge distribution is symmetrical. For instance, we have a infinite length of line charge, we have an infinite area of surface charge, and when we have a charge in the form of spherical structure, it can be in terms of spherical, surface charge density or the volume charge density. Okay, and the same things apply for the ACL, in which the ACL can be used to calculate the magnetic field intensity for the case of a special current distribution. Okay, so what is meant by special case of current distribution? So we're going to see it later in this lecture. Right. So this is a mere comparison between the Gauss Law and the Ampere Circuital Law. So if we base on this slide, we can see that for the Gauss Law, it can be applied if we have a source in terms of infinite length of line charge, and we have the infinite area of surface charge, and also in a form of spherical charge distribution. And for the case of ACL, these are what we mean by the special case of current distribution, where we can apply the ACL if your current distribution is in terms of infinite length structure of the filament current, or we can have the infinite area of the surface current. So these are the possible current distribution that can be used in calculating the ACL. In calculating the H field intensity by applying the ACL technique. Okay, and for the Gauss Law, we use the Gaussian surface in calculating the electric field intensity. So we need to sketch the Gaussian surface first before we can apply the Gauss Law. Whereas for the ACL, we need to sketch the Amperian loop before we can proceed with the calculation of the H field using the ACL. So these are two different things. For the Gauss Law, we have the Gaussian surface, and for the ACL, we have the loop, or we call it as Amperian loop. And this is the equation for the Gauss Law, where we have the Gauss Law is given to be a closed surface integration of d dot ds equals to the q enclosed. Okay, we have, I think you have understood this very much in electrostatic field study before. And for the case of ACL, this is the equation where we have the closed loop integration of h dot dl. Okay, so we call this as Amperian loop. Okay, h dot dl, closed loop integration, and that should be equals to the enclosed current. Okay, So we can see a difference here between these two equations. Whereas for the Gauss law, for the left-hand side, this is a closed surface integration. Whereas for the ACL, for the left-hand side, this is the closed loop integration. So we have a surface integration for the Gauss law, and we have a loop integration for the ACL. Yeah. Right. So let's have a look on the application of ACL in calculating the H field intensity due to a filament current structure. Okay. So looking at this slide, we have a case of infinite length of filament current. Yeah, we have a current having I direction towards a positive Z, and the length is infinite. Okay, and let's say you want to find the H field produced by this particular line current at a given location or any location. So the first step that you need to do is that you need to create a closed loop that surrounds the filament current, and this closed loop is what we call as Ampere loop. Yeah. Okay. So for instance, this is the Ampere loop that we shall draw before we can apply the ACL. So basically, you need to ensure that if you want to calculate the H field at this particular location, so your Ampere loop must pass through that particular point. Okay, so you need to remember that point. Yeah. So step number one, you need to create an Ampere loop that surround the filament current, and you need to ensure that the loop drawn must pass through the intended location that you need to find the H field. So that's the first step. Second step is that you need to identify the loop element, the DL. Okay, so in this case, this DL should be the element of the loop. So basically, the loop is given here in the diagram, which is a circular structure. So the DL by right should be somehow located on this particular dotted line. So that should be your DL. Okay, and from this diagram, we know that the DL should be equals to R d phi, the direction of phi. If we take that the radius for this loop is equals to R. Yeah, so your DL will be R d phi, direction of phi. And once you have identified the loop element, the DL, sorry, that should be a vector, yeah? That should be a vector, the DL vector. Once you have identified the DL, then only we can proceed with the ACL, which is H dot DL closed loop integration shall be equals to the IN closed. So if you base on this, we try to figure out the left-hand side equation, the left-hand side term. So this will be the integration on this particular loop, while the IN closed should be the current inside the loop. Okay, so let's have a look at the left-hand side first. Yeah. So for left-hand side, we're going to have that the closed loop integration of H dot DL. So this is for left-hand side. Yeah. H dot DL. Okay. So we know that from the given from the step number 2 just now, we have the DL should be R d phi, direction of phi. Yeah. All right. So we have that DL will be R d phi, direction of phi. So based on this, we can write that this due to the dot product between the H and the DL, so the H vector will be written as H phi, direction of phi. Yeah. Right. So when we proceed with this integration, a closed loop integration, we're going to have H phi. Okay, and the integration for R d phi will give us 2 by R. Yeah. So that should be the closed loop integration of the H dot DL. Right. Whereas for the right-hand side, okay, for right-hand side, which is the I enclosed, basically this is the current enclosed by this particular Ampere loop. So if you base on this diagram, you know that the enclosed current by the loop shall be equals to this current. Yeah, shall be equals to this current of I. So we can simply write that the I enclosed of this case should be equals to I. Right. So we have the equation for the left-hand side, the terms for the left-hand side, and we have the term for the right-hand side. And for this, we're going to have these equations here on this slide, where we can write that from the H phi 2 pi R equals to I. right? So from the previous slide, we have hv of 2 pi r equals to I. And from here, we can have that the hv will be equals to I over 2 pi r. Okay, and in the vector form, we're going to have the h vector can be equals to I over 2 pi r in the direction of v in ampere per meter unit. Okay, so this is basically similar to what we have obtained from the previous lecture 15 on the Gauss law, where this is the equation of H field intensity produced by the infinite length of filament current. Yeah, so we have proved now that by applying the ACL, we can have a similar equations of H as what we have obtained previously using the Gauss law. Yeah. Okay, so next we're going to have a look at this application of ACL for the calculation of H field due to a surface current. So in this particular example, we assume that this blue colored area is consists of your surface current, and we assume that the area is very large. Yeah, is very large, in which we can assume that this is it is approaching infinite size. Yeah, it's very large size. So we assume that on this particular surface current, there is a surface current density given by the Gs vector equals to Gs in the direction of y, in which we assume that the current is directed towards the y direction. Yeah. Okay, and you need to find out what should be the value of H field produced by this particular surface current at any position at the top and at the bottom of it. Okay, so the first thing that we need to do, as usual, we need to create an Ampere loop, knowing that you want to find out the H field at the top position here at this particular location, for example, yeah, just at the top of this surface current. So you need to ensure that your drawn loop, your drawn Ampere loop must pass through that particular point. Yeah, must pass through this particular point. So in this particular case, we are using a rectangular structure to represent the Ampere loop. Yeah, so that should be the loop that we need to draw. Yeah, which is a rectangular structure in the dotted lines here, right? So we assume that you want to find out the H field at this particular position. Okay, at this particular position. So then your loop must pass through the point here, that point there. Okay, so that should be the first step. The second step that you need to do is that you need to identify the DL for all of these loop dimension. I mean the loop length. Yeah, for instance, if we base on this, you're going to have 4 different DLs. Then we've related these Ampere loop supposedly. So we're going to have this loop direction. Yeah, from 1 to 2, the DL should be dx direction of x. So please refer to this axis, x, y, and z. From 2 to 3, we have the DL to be equals to dz direction of negative z. And from 3 to 4, we have the DL of dx direction of negative x. And finally, from 4 to 1, we have the DL of dz direction of z. Yeah, so that should be the DL with respect to each side of your Ampere loop. Okay, and for the step number 3, then we can use the ACL to find the H field as requested. Yeah, right. So that should be the case. So let's have a look. The ACL for each of the side. So we're going to have from the ACL we have the H dot dl integration shall be equals to the I enclosed. Okay, so we can see that for the closed loop integration, yeah, for left hand side, I just need to write the left hand side equation here. Left hand side, we have the closed loop integration. Yeah, basically for this integration can be written as a 4 different integration related to the sides of your Ampere loop, where we have integration from side 1 to side 2 of H dot dl, plus integration from side 2 to side 3 of h dot dl, from integration from point 3 to point 4 of h dot dl, and finally integration from point 4 to point 1 of h dot dl. Okay, so this is the loop integration, yeah, the closed loop integration, right? So if you base on this integration for each side, yeah, let's say we concentrate for the first integration from point 1 to point 2, right? So we can see that from point 1 to point 2, your dl has been given, yeah, which is dx direction of x. So we're going to have the dl to be equals to dx direction of x. And for the H field, yeah, for the H field, if you base on this direction of your current, yeah, and by using the right hand rule, yeah, right hand rule, we can deduce that the H field should be directed towards the x direction, yeah. So the right hand rule states that if you use your thumb, yeah, if you use your thumb as the current direction, so the rest of the fingers will give us the direction of the field, yeah, direction of the field. So based on that, we can say that the H field direction for the first side from point 1 to point 2 will be towards x. So then we can write that the H field should be written as hx direction of x. Okay, and for point 1, for point 2 to point 3, then point 2 to point 3, we can have that the H field, I mean the dl is given to be dz direction of negative z, yeah, but the H field, if we look carefully here, will be either directed towards positive x or towards negative x, yeah, for point 2 to point 3. So I just need to write here that for point 2 to point 3, your H field will be either direction of x or direction of negative x. Yeah, so this is based on the right hand rule concept. So based on this, if we have a dot product between the x unit vector and the negative z unit vector, we can then write that for point 2 to point 3, the dot product will give us 0. Yeah, so for point 2 to point 3, the h dot dl will give us 0. Yeah, and then from point 3 to point 4, we have that the dl is dx direction of negative x, and then by using the right hand rule, we can write that the h vector will be also directed towards the negative x direction, yeah, towards negative x direction. Yeah, so that should be our h vector for third side, which is from point 3 to point 4. And finally, for point 4 to point 1, we can say that this dot product will give us 0 because the nature of this integration will be similar to the integration number 2. Yeah, so we left only with the first integration and the third integration. And if you proceed with that integration, yeah, we can say that then this integration, if we assume that the length of this rectangular loop is equals to L, for instance, so we can write that this integration will give us 2hx of L. Yeah, so that should be the result of left-hand side integration. Okay, and for the right hand side, which is the I enclosed, yeah, right hand side, the I enclosed, we can say that since the I enclosed is in the ampere unit, and we need to find out what should be the current that is enclosed by this rectangular loop. Yeah, so if we have that this particular current flowing in your surface or on your surface is Js, in which Js is given to be in the units of ampere per meter, the surface current unit. So we can write that the enclosed current will be simply equals to Js multiplied with L. So that should be your enclosed current by this rectangular loop. Okay, so now we have the results for the left-hand side, which is 2hx of L, and right-hand side which is a Js multiplied with L. So then we can equate these left and right terms, and we have these equations down there. Yeah, if I can rewrite it for you, from the previous slide, we have 2 hx of L equals to Js of L. So L can be cancelled out, and we have then hx equals to Js divided by 2, which is given down here. Okay, and following this, we can simply say that if we are facing a problem of infinite area of a surface current, we can see that the H field intensity can be calculated simply by using this equation, where we have the H field intensity will be equal to half of Js vector cross the n unit vector, where the n unit vector is a normal unit vector related to your surface current, whereas Js here is your surface current density. So if we go back to this slide here, okay, and let's say you want to find out the H field intensity at the top surface and at the bottom surface of the surface current, and from the previous equation we have H vector equals to half of Js vector cross the normal unit vector. Okay, so for any point at the top of your surface current, we can say that the normal unit vector with regard to this point will be equals to z. Yeah, so normal unit vector will be equals to z unit vector. So from here, we can write that the half of Js, which is Js of that y unit vector, cross the z unit vector, and we can have the equation to be half Js of the x unit vector. So that we will have that the H field intensity for any position above this particular surface current will be half Js of x. Whereas for any position below the surface current, we can see that the normal unit vector will be equals to negative of z. Yeah. So for any point below the surface current, we can say that the H field intensity will be half of Js cross n, which will give us half of Js direction of y cross a negative z unit vector, and this will give us half of Js in the negative x direction. Okay, so this will be the H field above and below the surface current, which is infinite area, in which we can simply use the equation of half Js cross n to get the value of H field intensity.